So let's start off with the formal statement of the chain rule. And it goes like this. If we're taking the derivative of a composite function, so that just means that we have one function that's inside another one, that's the derivative of the outside function with the inside function untouched times the derivative of the inside function. So let's just write in words what that's saying. It's saying if you have one function inside another, take the derivative of the outside without touching the inside, and then multiply by the derivative of the inside. So let's kind of look at what this is talking about. Let's just take an example from earlier. We know that from our power rule that the derivative of x cubed, what we do is we bring down the exponent and then subtract 1 from the exponent to get that. The derivative of x cubed is 3x squared. Now what we're thinking about is we're imagining that this x here, this can be anything. So let's just imagine that it's a sort of a box that we put another function in, just like we did when we were reviewing composition. So this is really the same as saying that the derivative of something to the third power, let's just make that a little box to the third power. Whatever that something is, we're going to bring down the exponent, keep that something, whatever's in the box, and subtract 1 from the exponent. And then we're going to take whatever was in the box and take its derivative. And so whatever's in that box, after we use our normal rule, we have to take the derivative of what's in the box. If there's only x in the box, then the derivative of x is 1, and it doesn't really change anything. So let's imagine this scenario. Well, we bring down that 3, we keep whatever's in our box. And if this was x, well, this derivative here, the derivative of x is just 1, so it's just 3x squared. Doesn't change anything, it's just exactly what we had up here. However, if there's anything else in that box that's not x, or not just a plain old x, we have to make sure to take its derivative. It's kind of like a present that's got multiple boxes around it. You got to unwrap them all to get to what you're going for. So let's look at an example of that. Let's say that instead, so a separate example, instead of just having x in that box, we've got a 2x. We're still going to follow this same pattern. We're going to bring down the exponent, subtract 1 from the exponent, and then take the derivative of whatever is in that box, but now we've got a 2x here. So what we're going to have right here is we're going to have this 2x squared. And now we have to take the derivative of 2x, which is just plain old 2. And there we go. This is what the chain rule is saying. If we ever have something that's inside another function that's not just plain old x, we got to make sure to take the derivative. Now, there are only 4 types of functions that we've worked with that have boxes. Those are power functions, so if we ever have something that's x to the n power, that's some sort of box to the n. Trigonometric functions, so for example, sine of x, if we ever see that, that's sine of some box. Or if we had something like cosecant of x, that'd be cosecant of something in a box. We've also got exponential functions. So that would be like e to the x is really e to the box, or 2 to the x is really 2 to the box. And then finally, logarithmic functions. Natural log of x. We see that, we should think natural log of the box. Or something like log base 3 of x, we should be thinking log base 3 of a box. So when we start thinking about things as boxes, we have new rules that come into play. So these are based on our old ones, but they look just very slightly different because there's this new sort of box piece that we are going to be working with. So let's label these new rules, or really examples of new rules. Oh, one thing we should add in before we do this, looking back at these functions that got boxes on the previous page, I just want to add in functions consisting of addition and multiplication without any of the 4 types of functions that we saw here do not get boxes. So 3x plus 1, just going to sit and chill. Okay, coming back to our new rules. So if we have a situation where we're saying let's find the derivative of something to the nth power, that's going to be bring down the exponent, have whatever's in the box, and subtract 1 from the exponent. And then we also have to do multiply by the derivative of whatever's in the box. Same thing for any of the trigonometric functions. Let's take sine as an example. Could be cosine, could be tangent, could be whatever. Any of the trigonometric functions we've got the box next to, it's going to be whatever the derivative of that is times the derivative of whatever's in the box. If we've got e to the box, the derivative of that is e to the box, whatever's in there, times the derivative of the box. Natural log of the box, 1 over the box, times the derivative of whatever's in there. Notice this derivative is in the numerator, not the denominator. So the key thing here is that if you see any of these functions when we get to our examples, the first thing that you want to do is put whatever is showing up in the box. So anything that's taken to the nth power, put a box around it. Sine of something, put a box around it. E to the something, put a box around it. Natural log of something, put a box around it. So let's start off with doing a few examples. Let's say we want to find the derivative of 3x plus 1 to the 4th power. Notice this is something to the 4th power. So anytime we have something to a power, we're going to go and we're going to put the little box around whatever's being taken to the 4th power. Make sure you get the whole thing. It's this whole 3x plus 1. Now we're going to use this rule up here. We're going to take the derivative, bring down the exponent, subtract 1 from the exponent of whatever's in the box. And we're also going to multiply by the derivative. Of whatever was in that box. Now we look over here, what was in the box? It was 3x plus 1. So when we do this, we've got 4, 3x plus 1 cubed, that's just sticking around. And now we have to take the derivative of this whole thing. The derivative of 3x is 3. The derivative of 1 is 0, so we just add 0. Nothing happens there. Simplify by multiplying these together. And there we go. We do the same thing anytime we see any of the trigonometric functions. So like over here, let's say we want to take the derivative of the sine of 2x. We see a trigonometric function here, so whatever is right here is going to go in the box. And so that means that we're going to take the derivative of the sine, which is cosine, of whatever's in the box, and then we're going to have to take the derivative of whatever's in the box. In this case, this was 2x, and that's 2x. So cosine of 2x, then the derivative of 2x is just 2, or 2 cosine 2x. Right like that. This happens with all sorts of trigonometric functions. So if we say that we're doing the derivative, let's say of secant 4x plus 1, as soon as we see that trigonometric function, there's our box. We know that secant, the derivative is secant times tangent of whatever's there. So we've got secant of the box times the tangent of the box. And whatever's in our box, gotta come out and take the derivative. That was 4x plus 1. So we've got the secant of 4x plus 1 times the tangent of 4x plus 1, and the derivative of 4x squared plus 1 is just 4 from here plus 0, so just 4. the chain rule shows up in some places you wouldn't necessarily expect it. So let's say that we're taking the derivative of 1 over 5x plus 2. Now, this doesn't really look like any of the things on our list. But one of the things that we remember is that if we have something in the denominator, that's the same thing as rewriting it, saying we're going to take the derivative of 5x plus 2 to the negative 1 power. As soon as we have something to a power of, there's our box. We'll pretend that's a pretty box. And now we're applying the power rule, just like we were doing before. Bring down the negative 1. Subtract 1 up here, make sure that's negative 2, not 0. And multiply by the derivative of whatever was in the box. 5x plus 2, 5x plus 2. We have negative 1. This is 5x plus 2 squared in the denominator because of that negative 2. The derivative of 5x is 5. Derivative of 2 is 0, so there's nothing else there. Negative 1 times 5, remember this 5 is in the numerator. Negative 5, 5x plus 2 squared. We'll see this even with slightly more complicated problems. Let's give this one a shot. Let's say we want to find the derivative of the natural log of e to the x plus 3x minus 4. There's a logarithmic function, so that means that all this is in the box. We know that the derivative of the natural log of a box is 1 over a box. And then even so here we've got to do times the derivative of whatever's in there. Notice again this derivative is always in the numerator. It's never going to be in the denominator. So that was e to the x plus 3x minus 4. E to the x plus 3x minus 4. Notice we do have an e to the x right here, which is one of our box functions from over here. However, there's just a plain old x here. And if there's just a plain old x, then when we take the derivative of x, it will be 1. It's not going to change anything. So if there's just an x, we don't have to put the box around it. If we do, it won't cause any problems. It'll just be more work for us. So right here, we're going to take the derivative of this. This is still sticking around as 1 over e to the x plus 3x minus 4. The derivative of e to the x is just e to the x. Derivative of 3x is plus 3. Derivative of negative 4 is 0. So we get e to the x plus 3 over e to the x plus 3x minus 4. Let's play with another e to the x function. Let's take the derivative of e to the 5 over x. E to the is one of our box functions, so we've got a box here. So the derivative of e to the box is e to the box times the derivative of the box. So here's 5 over x, and we notice when we're taking the derivative that our life is way easier if we rewrite this as 5 times x to the negative 1, because then we're allowed to use our power rule. Notice again that we have a power function right here. We could put a little box around the x. However, it's only an x. The derivative will be 1. It's not going to change anything. So if there's only an x, there's no need to put that box around it. So here we've got e to the 5x. Now we're going to take the derivative here, bring down the negative 1, that's negative 5. subtract 1 from the exponent, right there, e to the 5x times negative 5 over x squared, or negative 5 e to the 5x over x squared. One final one, and then we'll do our check for understanding problems. Let's take the derivative 4x squared plus 3x minus 2, all of that to the 7th power. We notice that we've got a power function, so we're going to have a box here. And that means that we're going to bring down our exponent, subtract 1 from the exponent, and then multiply by the derivative of whatever was in that box. When we take this derivative, we have a power function right here. We could do a box, but there's only an x, so we don't need to. So we can just use our normal rules, bring down that 2, multiply to be 8, subtract 1 from the exponent, and then the derivative of 3x is just 3, the derivative of negative 2 is 0, and there we are. Okay. Let's do 2 check for understanding problems now. 1, I'd like you to find the derivative of the tangent of 2x. And for the other one, I'd like you to find the derivative of the sine of x plus 4x plus 9 squared. Do those on your own. Resume the video when you're ready. Pause the video now. Okay, here's what I saw. I saw that we had a trigonometric function, so there's a box right there. We take the derivative of tangent, which is secant squared of whatever is in the box, and then we multiply that by the derivative of whatever is in the box. The derivative of 2x is 2, so our final answer is secant squared 2x times 2. Here we have a power function, so this whole thing that's being squared is in the box. We bring down the exponent and subtract 1, put whatever is in the box right there. Then we take the derivative of what was in the box, which the derivative of sine x becomes cosine x, derivative of 4x becomes 4, the derivative of 9. One thing to notice is that when we're doing the chain rule, coefficients are along for the ride. So just write that. Let's say we had the problem, find the derivative of 3 times 2x plus 1 to the 4th power. And let's just look at that versus finding the derivative of, let's say, 3x to the 4th power, one of the old type of problems. So notice over here we have a box function. So that means we're going to use the chain rule when we're taking the derivative. In this case, the 3 is just along for the ride. Just like over here, the 3 would be along for the ride, and then we would do 4, bring down the exponent, subtract 1 from the exponent to get 4x to the 3rd. Same idea here, we bring down that 4, just like we did over here, except that now we also have to do the derivative of what was inside the box, that 2x plus 1. However, the key thing is that this 3 here is along for the ride, just like this 3 was along for the ride here. That being the case, we've got 12 2x plus 1 cubed times the derivative of 2x is 2, derivative of 1 is 0. This is 12x cubed over here. Multiply these together, 24 times 2x plus 1 cubed.